For the third lecture, we continue to study the inversion method, and we shall begin with a more formal study of probability density function, or PDF. So let x be the random variable, and we say that x follows the density f of x, so that f of x can be defined as the density of the random variable x, so that it is the limit as delta x go to 0, the probability that x fall into this small bin from x to x plus delta x divided by the size or the length of this small bin delta x. So that is the probability mass divided by the size of the small bin. It is like you smear the probability mass uniformly over this small bin. And as delta x go to 0, we get the notion for density, which is in the unit for probability mass divided by the unit for the size of the length. And then from here, we say that the probability that x fall into the small bin is f of x times delta x. So if we plot f of x, then f of x times delta x will be the area for this small rectangle. Okay, so this is a more or less formal definition for this density and its relationship with the probability. So the probability is density times delta x. So here we put a dot here, meaning that there's a discrepancy that is smaller than delta x. Or in other words, we consider delta x to be infinitesimally small. So this is a common way of doing things in calculus. And given the probability density function, we can then define cumulative density function, f of x, big F, which is defined as the probability that the random variable is less than or equal to small x. So for this any random variable or any value of x. Okay, so I don't know what the meaning for that. So x is actually any number. It's not really a number. It's random. So this x, this big X, is a random number or random variable. So maybe we should switch these two. So this small x is endpoint here. Okay, this small x, and big X is a random variable. Okay, maybe we should switch here and here. Okay, sorry about that. And then we can define this as the area under this curve to the left of this endpoint x. Okay, and then we can write this as integral from negative infinity to x, fx dx. We don't need the parentheses, so this is just a dx. And here we are abusing the notation a little bit. We use x for the endpoint, and we also use this x, the same x, for the random variable goes from negative infinity to x. You can change this to ft dt if you feel that's more comfortable. But in any case, f of x is the area to the left of this x. So therefore, if you increase x, you are going to increase the big f of x. So you are accumulating this density. And if we look at the relationship between this CDF, cumulative density function, and the PDF, the probability density function. So this is CDF. It changed from 0 to 1 as we increase x, right? And in the previous page, we say that this big F is actually the area under the curve, so that it is an integral of small f. And conversely, small f, the PDF, is the derivative for the big F. So the reason is that if we look at the derivative, it is actually the limit as delta x go to 0, then f of x plus delta x minus f of x divided by delta x, right? So this is how we define the derivative. So if we look at this f of x, so if we have x here and x plus delta x here, then we see that the change for f of x, which is f of x plus delta x minus f of x. So we can call this as a delta f of x, the change of f of x divided by delta x. So that will be the slope. Okay, the slope. And then we can write this as f of x is the area to the left of x plus. So here x plus delta x, right? So that's area to the left of x plus delta x. And f of x is area to the left for x. So if we look at the difference will be the area within x plus delta x. And this area is exactly or approximately f of x delta x. And if you divide this by delta x, you get f of x. Okay, so that is big F. Big F here, big F is the integral of small f, or the area under the curve small f to the left of this endpoint x. Okay, so this is so here in this plot, big F is the integral, and the change delta f is the area of this small b, okay, in this plot. But if you look at this plot, so here this curve is about big F, so that delta f will be the change of the height. Okay, so the change of the height here is actually the area of this small beam. So that's how we look at the things. So basically, the slogan is that the integral is really just area, right? The integral is area, and the derivative, like here, the derivative is the slope. So the derivative is a slope. Okay, but when you plot f here, then the change for the f, then it's just a change of the height. But if you use this plot, you plot small f, then the change for the big F is this small area. Okay, so these are just some simple calculus concept, but I think this geometric concept is very useful for understanding the basic idea for calculus. And we can also write small f to be df of x divided by dx, which essentially saying that here, right, when we let the delta x go to 0, then according to the notation for Leibniz, so this becomes df of x divided by dx. And we can sometimes also write df of x, the change of f of x is small f times dx, because from here you see this one equal to f of x times dx. So last time we introduced this inversion method. So that is, we want to generate this x from this density x, okay? And the method is that we first compute the cumulative density function, big F, which is integral from -infinity to this endpoint x, and then the integral of this function. So the area under the curve of this function to the left for this endpoint x. Okay. After you compute that, you then compute the inverse of this f. So what we mean by the inverse of f? So it means we want to solve this equation, f of x equal to u, so that x equal to f inverse u. So x is a solution to this equation. Okay, and why we use the notation inverse? The reason is that the reason we use this notation is because if you look at the, you apply this big F, and then you apply F inverse, then F inverse f x equal to x. So that is F inverse times F is identity. It's not really identity matrix, it's identity mapping. We may use I to denote identity mapping. It's not necessarily a matrix, not necessarily linear, can be nonlinear. But in any case, you see that if we call this identity mapping to be 1, so then this F inverse times F equals 1. So that makes a lot of sense, right? So that is where you can, in algebra, we can use x to represent any number, but we can also use this f, the symbol f, right, as if it is a number, and then we can invert it. So we're just making things more abstract. So that is here, this symbol represents actually a mapping, and F inverse is the inverse of this mapping. So it doesn't mean F inverse doesn't mean it's a 1 over something. Okay, so it actually means the inverse of this mapping. So that is, we find the solution to this equation. Geometrically, it means that if you have this f of x, big F, and if you have u, you can retrieve this x by first going horizontally to hit this curve and then go down to retrieve this x, so that now you see f of x equals u, right? So you solve this equation to get x, which is a matter of getting the inversion. So therefore, the algorithm for generating any random variable that follow the density f of x is to first generate u from uniform 0 to 1, and then we return x to be f inverse of this u. Okay, so that's the inversion method as we studied last time. So this time I want to give you a more concrete idea about this inversion method. So first, what we mean by PDF, f of x. So we say that a random variable x follow a probability density function f of x. So how do we visualize this f of x? What's the underlying intuition? Well, we can still think about random sampling of a population. Suppose we have a population of 300 million. So we use this number just to be concrete. So this is a number of people in US, but essentially we let this to be a big N, the total number of people. Then this big N is approximately or almost infinity. So that's how we think about it. It's an extremely large population. We randomly sample a person and we get the height of this person, and we let X to be this the height of the random person. Then we say f follow f of x if f of x describe the distribution of the heights of this 300 million people. In other words, you can look at this population version of the scatter plot. So here, there's nothing random. We have this 300 million people, and we plot this 300 million people on the x-axis according to their height. So each person in this population become a point. And let's assume that we actually measure the height in infinite precision. We don't just stop at inch. We continue to use fine and finer units with infinite precision. And then we have this collection of real numbers, 300 million real numbers. And then you can think of this density f of x is a density of this population. So here there's nothing random. So what do we mean by this density? How can we make it more concrete? Well, you can let the total number n to be 300 million. That's the total number of people in the population. And we let n of x to be the number of people in this small bin, for example, from 6 feet to 6 feet 1 inch, if delta x is 1 inch. So we look at what's the number of people in this small bin. So this is actually a slice of the population, right? All those people within 6 feet to 6 feet 1 inch, for example, that's a slice of the population. So if f of x is the density of this population, it means then this number, the number of people in this range is total number n times f of x delta x. In other words, f of x delta x is the population proportion of the people in this range. Or more specifically, f of x then is defined as the population proportion divided by delta x. And here again, n here is 300 million, but we can say n is almost infinite when we think about this, this problem. And then for this probability density, or for this population, so that the density describe the distribution of the points in this population. So there's nothing random. And we can also define f of x, big F. Big F then count the number or the proportion of the population below this x. Okay, so again, there's nothing random. It's just for each x, we just count what's the proportion of the population that below this point. Okay, so this f of x is a cumulative density. And and then we can also think of, say here, you see it is denser here, right? The points are denser here, so the density is high, and it's less dense here, so the density is low. So that is, when you think about the density, you can always imagine a population of points, so that how dense the points are distributed at each point give us this density, or the density tells us how densely the points are populated. Just like the density of the US population, so it is dense in LA, perhaps even denser in UCLA, right? So we just look at the proportion of the people in LA divided by the area of LA, we get the density of LA. And then if you look at the whole country, in different places, you have different density. And here we look at the one-dimensional situation, and then at different places, we have different density. So here there's nothing random. But when we have randomness, when we do the random sampling, we randomly sample person, or rather we randomly sample point among this 300 million point. And then we look at what's the coordinate of this point. It's like we randomly sample the person and what's the height of this person. So this height clearly is random, and this we say this to be a random variable. The height of the random person is a random variable. It follows this density because it's sampled from this population that follow this density function. Okay, so that's how we visualize or think about this intuitively. Okay, now you can think about how to do the random sampling. So the population is a fixed, deterministic, but we get the randomness when we do random sampling. And how do we do random sampling? So you can think of, we order the people by height, because we assume that we measure the height in infinite precision. So it is essentially zero probability that the two people have exactly the same height to all the precision. Therefore, we can order the heights we can order those points according to the heights, right? So this first one, the smallest one, second smallest one, and this big N is the largest one. And there's no tie because for real numbers, as I say, the probability of a tie is essentially zero. So now you see we number all the people in the population, all the 300 million people in the population according to their height. And then how do you randomly sample a person? You just randomly sample a number uniformly from 1, 2 to n, right? You have n numbers, you randomly sample a person from this 1 to 2, 1, 2 until n. Okay, so that is here. You randomly sample a person, sample I, which is a uniform distribution over these n numbers. Okay, because you ordered people according to their rank or their order, right? So you randomly sample I, and then you let x be the height of the ith person. Okay, so that's how you do a random sample, right? You randomly sample a person from this population of 300 million, or you randomly sample point from these 300 million points that follow the density f of x, or f of x describe how the distribution of these 300 million points. And now, if we sample I uniformly from 1 to n, then if you look at U to be I over n, then it follows a uniform distribution from 0 to 1, right? So let's assume n is big enough, then I over n can be treated as a real number, and it follows a uniform distribution. And this U actually is just a percentile of this person, just like in the SAT score, as I mentioned last time. So if you tell me the score, you also can translate the raw score to the percentile, right? So the percentile is like if you are the ith person, so your rank is I, and I divided by n, this gives you the percentile. That is what's the percentage of the people that below you. Because I follow the uniform distribution from 1 to n, so I over n follow a uniform distribution from 0 to 1 if n is large enough, so that we can treat I over n as a continuous real number. Okay, and then you want to get x to be the height of the ith person, which means the population of the people below the ith person is U, I over n. And then that means f of x, which is a proportion of the people below x, right? That's our f of x. The proportion of people below x is I or n because we sampled ith person. So this I or n is u, okay, it's a percentile. So therefore, given this percentile, and we want to retrieve the height of this person. So we have f of x equals u. So that is because you sampled ith person, and the percentile is u, which is I over n. And that means that the proportion of the people below this score x. So this is, suppose this is ith person, and this is the score is x, and actually I just moved this cloud points here. I think this can be more carefully drawn. So you have those points. So this is ith point. So this is ith point. We order the points from 1 to I and n. So this ith point was a corresponding value of x. So you have the order, right? You have the rank, but you also have the height. For example, this may be 6 feet. So what is value? So now you see that the proportion of the points below this ith points is exactly I or n, right? I or big N. And I or big N is our U, which is uniform distribution. And then we know that the proportion below this x is exactly f of x. So then we have fx equals u. So this tells us what the corresponding height of the ith person. We just saw f of x equals to u. So that means this x is exactly the ith person, right? The order of this x is I. And then we saw x to be f inverse u. So therefore, if you look at this whole step, so you run you first order all these 300 million points, okay, and then you randomly sample a I from 1 to n. So that means you randomly sample point, and then you retrieve the corresponding x. So this is our understanding. So we have a deterministic population described by f of x and big F, right? And from here, and then you do the random sampling. This part is totally deterministic. There's nothing random. But if you do random sampling, you get a random person, right? As if you randomly sample point. And this is accomplished by randomly sample I from 1 to 2 to n. And then you retrieve the height of the ith person. And what we are doing is exactly doing here. So we have u follow uniform 0 to 1, and then we have f of x equals u. So we retrieve the height of the ith person to be f inverse u. So that is, if you tell me your percentile of SAT score is 99%, then I can retrieve the corresponding score. It is basically the same idea. Okay, now let's move on. So we can actually prove this more formally. So suppose we have random variable x follow f inverse u, and we want to know what's a cumulative density function of f. So this f is a cumulative density function for the target distribution that we want to sample from. And we generate x follow f inverse u. We want to know whether the cumulative density function of the generated x is actually indeed the big F. So to this end, we compute the probability that the big X is less than equal to any fixed small x. So this probability is the same as saying that if you look at this plot, so this is our big X, and if the big X is less than or equal to small x, then the corresponding u, the corresponding big U is less than equal to f of x. And u is a random variable uniform from 0 to 1. And f of x is a fixed value. Here u is random. F of x is considered fixed relative to the randomness of u. So if, say, this f of x is 0.7, what's the probability that u is less than equal to 0.7? That is exactly 0.7, right? In general, for any f of x, then this probability is f of x. So here, relative to the randomness of u, f of x is a fixed value for each fixed x. And then this probability is f of x. So here we actually prove formally that the cumulative density function for the returned x is indeed big F, which is exactly what we want. So the cumulative density of generated X is not a small x, is big F, this big F of X. Sorry for the typo. So this is how we understand the inversion method and how we formally prove that the inversion method indeed generates random variables that follow the desired density. So we can repeat the code so that we generate a sequence of independent and identically distributed random variables following the pre-specified density function. And we can also take another look at this method from the perspective of discrete random variable and the discretization of continuous random variable. So let's go back to the discrete random variable. Suppose we want to generate a biased die with a probability mass function. So P for 1 is P1, P of 2 is P2. So here, this is a geometric illustration of a probability mass function. So the height of each bar tells us the probability of the probability mass on a particular point. So here we assume that the die is biased towards bigger values. And then you can divide the range from 0 to 1 into 6 intervals of an equal length, so that the length of each interval corresponds to the probability, and the sum of the length of all the intervals equals 1. And then what we do is we randomly throw a point into this unit interval from 0 to 1, this big interval, right? And depending on which small interval it falls into, we return the value, which means that we return x equals k if this u, the generated u, the point that we throw to the unit interval, so this u is bigger than the summation from p1 to pk minus 1, but less or equal to p1 to summation p1 to pk, so that it falls into the case interval, right? So if u falls into the case interval, it means u is bigger than p1 plus until pk minus 1, but less than or equal to p1 plus p2 until pk. Okay, so in other words, we return k if u is bigger than f, this big F, k minus 1, which is how we define this big F, less than or equal to f of k. Okay, but for continuous random variable, what should we do? So you have this density function, and we know that the probability that the random variable fall into each small bin, okay, each small bin is area of this small bin, right? And let's order, or we suppose we divide the range of this x into those endpoints, equally spaced points, x0, x1, x2, until the big number, the biggest value is xi. And then we divide this range into, I'm suppose here the tail is so small, we can neglect it. So, and then we have this m small bins with probability p1, p2, p3, and pi. Okay, and then we can think of a discretized version. So that is, we have this discretized value x1, x2 to xm with the probability p1, p2 to pm. In other words, supposedly pk is the probability of the k spin, right? But for a continuous random variable, the continuous random variable can be anywhere in this small bin. We may even assume that it is uniformly distributed in this small bin. But for discretization, we just assume that it's equal to the right endpoint, xk. So in other words, we concentrate all the probability mass on xk instead of smear it uniformly in this small bin. This gives us a discretization. And the point is that if delta x, that is the bin size, becomes smaller and smaller, then this discretized distribution will eventually be considered as a continuous random variable, follow this density function. Okay, so now you can think of, again, we can divide okay, we can divide this range from 0 to 1 into this m small intervals. And the length here, the length of the case interval, pk, will be the area for the case bin. Okay. And because we want to generate a discrete random variable, this is a discretized version with this probability similar to this biased die situation. So that is, we still divide this unit interval from 0 to 1 into m's small intervals, and the length of each interval is the area of the corresponding bin. Okay, and this way, then we can, for example, we can randomly throw a point into this unit interval, and if it falls into the case interval, we then return sk. Okay, and just by the same logic here, so we return xk. We return xk if this u, the point that we throw onto the unit interval from 0 to 1, is bigger than p1 plus until pk minus 1, but less than or equal to p1 plus until pk. Or in other words, if u is bigger than f of xk minus 1, so that's how we define big F of xk minus 1, all the probabilities to the left of xk minus 1, but less than or equal to f of xk. But if we let the delta x go to 0, so we want our bin to be finer and finer, then we return x equal to xk here. If this is the bin size is very small, then practically we have u equal to f of xk, because these two are essentially the same. The difference becomes smaller and smaller. So we have u equal to f of xk in the limit of delta x go to 0. Okay, so that is from here we see that we return this x, right? Then f of x equals u. So x is f inverse u. Okay. So therefore you can also understand this inversion method from the perspective of discretizing the continuous random variable. And you can also compare the continuous cumulative density function with the discrete cumulative distribution function. So in the discrete case, the big F is a staircase function, right? As we showed in the first lecture. And in the continuous case, it becomes a smooth function, monotone increase from 0 to 1. And this is actually, you can think of this smooth function as a idealized limit of this staircase function when delta x goes to 0. Okay. We can also think about this inversion method as a special case for transformation of continuous random variable. And again, let's look at the uniform distribution. And for uniform distribution, the density is 1 within the interval from 0 to 1, right? And as I mentioned before, we can visualize a density function as a population of points. And for uniform distribution, we can also visualize this as a population of points. And indeed, this is actually true because in computer, when we generate pseudo-random variables using linear congruential method, we actually generate uniformly from this 0 to m minus 1, right? And we divide this by m, so that we actually, you can think of uniform distribution over 0 to 1. It's actually a uniform distribution over this m different values, right? 0, 1, and until m minus 1 divided by m. So we have this equally spaced values. So here the plot is not really uniform. So we should plot those points uniformly distributed. But the point is that we can then map. So suppose that we have endpoints, right? A population of endpoints uniformly distributed from 0 to 1. Again, apologize for this drawing. So suppose those points should be uniformly distributed. And then we map this big endpoints to the big endpoints here, which follow the density f of x. So here, this is uniform, but this is not uniform. You see here, it's more concentrated. So the density is like this, right? So you have high density in this range, but less density here. And but in any case, suppose we have endpoints here and endpoints here, so we can consider a mapping. So so that each point here is mapped to a point here. So at the simplest mapping is that we try to preserve the order. So we map the first point here to the first point here, and the second point here to the second point here, and so on. And the nth point here to the nth point here. So you preserve the order of the percentile. So this may be the ith point, right? And you map this to the ith point here. And this way, after this mapping, you are mapping the uniformly distributed points to this non-uniformly distributed points. And how this mapping look like? So suppose this is ith point, this ith point, then this should also be the ith point. And then suppose that this number is u, the ith point is u, which means the probability, because the uniform distribution, right? So the probability or the proportion of the points below this u. So what's the probability that a uniform random number is less than or equal to 0.7, for example, and this is exactly 0.7, right? So that is, if this is u, the proportion of the points below this u will be u, okay? And but then if this is x, if you map this u to x, then because this is also the ith point, right? So the proportion for the points below this x should also be u, and the proportion of the points below this x is f of x. That's how big F is defined, and this should equal to the proportion below this u, which is u. So therefore, we have fx equals u, so that f is f inverse u. So that is now you see that we can generate this x by mapping a uniform random number to this x. Or in other words, we have this big N for uniformly distributed points. Okay, by this mapping, it mapped to this non-uniformly distributed points. So let's call this mapping to be G. This G is actually exactly f of inverse. So this is actually an example for the so-called generative model. For example, in deep learning, if we want to learn to generate face images, so we can learn a mapping G parameterized by a neural network. So this G is sometimes called the generator network. And then the input U consists of not a one uniform random number, it may consist of, say, 100 independently distributed uniform random numbers. And this is essentially a vector. And this is G that map this 100 numbers to a image X, which is a face image. So it's something like that. So you often we call this as a generative model. Okay, so that's the mapping. So here, I hope that this mapping idea can illustrate the idea that we can map a set of points, a population of points that follow a certain distribution to a population points that follow a different distribution. Okay, and then we can also think about this inversion method from yet another perspective. So that is, you can imagine that this is our f of x, and then this is 0 to 1, right? 0 to 1. So you can think of consider the uniform distribution as endpoints that are equally spaced. And each point you retrieve the corresponding x by going horizontally first, hit the curve, and go down to get your x, right? And now if you look at if here we have those uniformly distributed lines, so those horizontal lines, they are uniformly distributed, or we have a equally spaced points on this vertical interval from 0 to 1, so that when we go vertically, so those rays are uniformly distributed, and then we go down, right? But if you look at this this horizontal rays, or if you look at the distribution of the corresponding x, then x is not uniform anymore, even though u on this vertical interval from 0 to 1 is uniform. But after you do this mapping, the corresponding x is not uniform anymore. Okay, so here, this is an illustration. So suppose you have the slope here, right? And then if you have if you retrieve the corresponding x, so you have equally spaced u, right? And then you get this x. You see it is quite dense here. But if you have equally spaced u here, but if the slope is low, and if you get your x, then it is less dense, right? It's quite sparse. So that is the density after this inversion mapping actually is determined by the slope of this curve. And the slope of big F is exactly the density small f as we discussed before. So the slope controls the density for the points on x. Okay, and this slope is exactly the small f. So therefore, if we generate the points on x in this way using the inversion method, we get the desired the density. Okay, because this is what is given, and based on, and then we use the F inverse to do this mapping, and then we get this the distribution of x follow the target density small f. So for just one example, think about the exponential distribution where the density f of x is e of negative x for x bigger than or equal to 0, and it is 0 otherwise. So that's the density. So supposedly you can imagine that you have a large number of points, say n points, big n point, n is almost infinity. And then you have a lot of values here, but less value here. So that's what this density tells us. So you can think of each point as a waiting time, a decay time of a particle. Suppose you have a population, big population of particles, then you know this is a decay time for a one particle. And if you plot all this population for n decay times, you get such a distribution. You have more points here, less point here, according to this density function. So if we are to apply the inversion method to generate a random variable follow this distribution, or in other words, we randomly sample point from this population of points follow such a distribution. So first, we compute the big F, which is an integral for this density to the left for x. So from 0 to x, e of negative x dx. So the indefinite integral is negative e of e negative x. And then you compute the definite integral. That will be 1 minus e negative I, x. So you want to then compute, you then want to get f inverse of x, right? So you want this equal to u. No, this is not f inverse. This is f of x. Sorry, this is a typo. This is f of x, which is 1 minus e of negative x equals u. Okay, and then you want to solve it to get the inverse. And then you get 1 minus u equal to e of negative x. So x is negative log 1 minus u. So this is f inverse u. Okay, this is not there's no inverse here. So this is f inverse u. And then you can use inversion method. You first generate u from uniform 0 to 1, and then you return x to be, this should be capital X, to be negative log 1 minus capital U. Okay, so that's how you generate this x follow such a distribution. And then if you now look at this method, so you follow uniform 0 to 1. Then 1 minus u also follow uniform 0 to 1. So therefore, you can just use u here, and then you don't change the distribution because u and 1 minus u, they have the same probability distribution, okay, or they have the same density function. And then you can just use x equals to negative log u instead of negative log 1 minus u, right? And from here, you have u equal to e of negative x. So that is, if you plot u here, u is e for negative x. So the mapping is that you have the uniformly distributed u, right? U follow uniform distribution from 0 to 1. And then if you look at the corresponding x, then you have denser points here, right? Denser points here, but less dense here. So that is, it follows the desirable density function. So this, you see, this is a transformation. In fact, all the transformations that we shall study are those differentiable continuous transformations. And those transformations will change from a uniform distribution to a non-uniform distribution. Another example is a normal 0, 1. So this is the most important probability distribution called the standard normal distribution. So the density f of x equal to 1 over square root 2 pi e of negative x squared over 2. It follows this bell-shaped curve. And the area between negative 2 and 2 is 95%. So in order to apply the inversion method, we need to compute f of x, which is area to the left of x. But more importantly, we need to compute the inverse of f. So that's f inverse u, so that fx equals u, right? We want to solve this equation. And in fact, we cannot compute f inverse, or we cannot compute f or f inverse in closed form. There's no closed form formula. But we can still find good approximations. Say f inverse u can be approximated by this formula for u between 0.5 and 1. And then for those u less than 0.5, between 0 to 0.5, you can use this formula to get the corresponding f inverse. And with this approximation, as in the homework, you can then apply the inversion method. Again, you generate u from uniform distribution from 0 to 1, and then you plug in, you let x to be f inverse u. You plug in this u in this formula, and you of this formula, then you get the corresponding x that follow this normal density. So in the homework, I asked you to implement this method. So this formula is just one of many different formulas for approximating f inverse. There are also a lot of formulas, even more formulas for approximating f of x. But in any case, for numerical methods, people develop different accurate approximations, and then we can use them to do this to apply this inversion method. Okay, so I think in this today's lecture, for this lecture, we studied in depth this inversion method. In particular, I hope that I convey you the basic idea of how to think about the density as a population for points, so that the density tells us how these points are distributed, where the points are denser, where the points are less dense. So just like the population density in US, right? So this density, and then randomly sample a random variable follow density is like a randomly sample a point from this population of points. So this is how we think about this in a more tangible way, so that everything become just counting, right? Counting the number or proportion of the points in the bins. And then we apply some calculus mechanism. For example, use the infinitesimal delta x, and then compute the derivative as a slope, and we compute the integral as the area by accumulating the small bins. So those are the basic idea. I hope that you will gain a intuitive understanding for probability density function, and also their continuous differentiable transformation. So under the transformation, we can change one density to another density. But it just means that this transformation is like a mapping. It maps one population of points to another population points, so that the density will change. In the next lecture, we shall study more carefully the change of the density under the continuous differentiable transformation. But we can stop here for this lecture.